Okay, so we get there, we have hold up, we missing is PS, slippage between life and education. Okay, let's see on flow regimes. Yeah, we have several different flow regimes. So on the X is the increasing plus flow rate to the right, and we'll see some of the different flow regimes. So this one is very low bubble, and then you have bigger bubble, fast bubble, and then you have more bubbles coming in, and you have something like more like a slug, and we have slug flow, and then we have a oh, what's so it's that again, yeah. So it's gas in the liquid. So gas is lighter than the liquid, so it's going faster. So you might see bubbles of gas, and you'll be looking like slug, and a bigger slug. So you might see like not continuous, and yeah, at the end,
Does it make higher the gas, higher the bubble?
yeah,
Yeah. Okay.
yeah, higher speed, higher velocity, higher bubble, and the more gas will be bigger bubble, and it will be like slug.
Mm. So the annular flow is considered
Oh,
more
it's very high.
very high.
It's very high gas, and therefore the liquid is just on the side.
Okay.
So then in that case, then the conventional tool, our conventional hold up will not be detected because it's on the side. So we'll detect maybe 100% plus. So that's the possible thing. And the increasing gas velocity, you may see the difference of the flow region. Yeah, we might also the same thing like this. So you start with the bubbles, small bubbles, and you have a bigger bubble, will be like collecting the bubble, become a slug, and sometimes it's not continuous, homogeneous, then it will be like a churn flow, and then the annular is like a mist. So annular mist, maybe you might not be seeing the liquid content. That's for vertical. Yeah. Horizontal, you might be dealing with the different flow region. It's more complex. But yeah, it might be like segregated. It's very stratified. It's okay. You can see this one here. If your spinner is in the middle, that's fine. You can read the water, you can read gas. And there is no slippage in this case. It's 90 degrees. Wavy, yeah, if you have a higher water rate, maybe like wavy like this. And yeah, annular, maybe the picture is not like that, but yeah, this is like the same like annular flow on the vertical. Yeah, because it's very high gas flow in. So you might see it's like a mist. The liquid will be forming like a mist or just a small thin film on the side of the wall of the pipe. It's very hard to detect. Or it might be something like intermittent. If the rate are high and the velocity of both phases are big, then you will be like continuous flow regime. But if you see a small rate of the gas, so it's maybe like slugs of gas on the top side. Or you might be having like bigger slug. So there's something bigger slug is coming in, and then no wood, no gas, and then no then a gas again. So it might be like that. Oh, yeah, you might be also you have a smaller bubbles like this. So you might have some different stuff. Back then previous, you can see this is back X-ray. Yeah, this title at all, dark title. So you might have a different name, different correlation, different flow regimes, different velocity of slippage.
Can we know after the analysis what type of flow we have?
Yes, based on the slippage, We need to know the type of the flow and we calculate the slippage based on the flow regime.
Okay.
So that's why we need to get the holder to get the flow regime.
Okay. But slippage meaning is the opposite of the flow.
Tak lah.
Bukan?
Slippage meaning the slip between light
Different phase.
and heavy.
Okay.
Seberapa dia lebih cepat.
Okay.
How faster the light
The lighter
compared to the heavy.
heavy. Okay.
Ya. Kalau dia sama, if dia same velocity, ya, slippage is zero.
slippage.
Yeah. For example, between oil and water, usually they are all the same liquid. You might see very small slippage, very small slippage. But between gas and liquid, you might see big slippage.
Okay.
Yeah. So when you deal with oil, water, it's just usually it's very straight line, so not really slippage between water and oil.
Okay.
So either oil bubble in water or water bubble in oil. Something. So this is Dun and Ross. It's one of the flow map. You can see on the Y is the light phase velocity. On the X is the liquid. So that liquid is gas. L is liquid, G is gas. Yeah. So on the left side, you have a small gas velocity. You might see bubbles, right? And then the bigger velocity of gas will be like a slug first, and then you will be like a big slug, and at the end it's like it's long as you see that. But it's only one dimensional. But if you have some different liquid velocity, then you might have a different transition level. It's not very straight line. The different flow regimes. Yeah, like this. So you have bubble of gas, block of gas, and we'll be having slug of oil. Yeah, you have slug of oil there, the green one in the middle. And then you have a mixed flow of the liquid in the gas. So this is just one Dun and Ross flow map. So you might have a different area determined by the line. You have a different flow regime. So you might see this is a calculation. So basically, NLV is the velocity of the liquid. Yeah, superficial liquid. So liquid velocity. There you have the constant there. So raw liquid divided by the theta is what you call it the interfacial tension. Yeah, so that's the constant. So it's proportional to the velocity of light and gas, or liquid and gas. And you might see L1, L2, whatever it is, you might go to the paper here, the F2 paper, you might see some definition of that one. So you define the line. Line is defined. And you might see this is the function of phase velocity, we know that one. The higher to the right, the higher the gas rate. Also on the Y, the higher the top, the higher the liquid rate. So it's another quick properties. You will be seeing the density, and you might see that's the rho L. So it's depend on the density of the liquid. By D you will be seeing this deviation. So yeah, you might have several parameters in this plot. Dimension of the slip rate. Okay, so this is the S test. S. The S is the slip rate. S is dimensionless. So just 10 times this constant that we've seen for the X and Y axis. So you might see this S there, where is the calculated dimensionless slippage, and then you times divided by the constant, you'll be able the PS, velocity of the slippage velocity. So yeah, it's really depending on the slippage calculation. They have different calculation formula equations. So the definition might be different between the correlations. and you might see S, and then S is 0. So in the mist flow, we assume there is no slippage. Why? Because the liquid is very small. So the liquid velocity will be the same as the gas velocity. Yeah, so that's the assumption that we have. Mist flow, no slippage.
Yeah, so we selecting the model for the what kind of model like a couple or a slug or a mixed flow, only the impact to a sleep rate.
Yes, yes, because you see different region, they have different formula. So the problem is you are in the transition. If you are in the transition, whether you use this region or the next region. So you have the choice.
For example, the transition is the mixture of slug and
Velocity. This is good. And is velocity, velocity of the gas, velocity of the liquid. So if the velocity liquid and the gas is falling this point, then you'll be choosing this region or that region.
Oh,
Yeah, because there will be different formula. Of course, they are not continuous. Well, continuous in that region, but not continuous in the transition. Yeah. So we need to define the flow regime. Yeah, we know if we know the flow regime, we calculate the slippage, and then we can have this liquid and gas velocity. This one is just when you do the nodal, yeah, just for nodal. But yeah, we have the granite as the nodal package or nodal module. So you can see the difference of the pressure drop or what you call it flow correlation. Yeah, we might have the square or the data that we have from the well, and we try to manage which correlation will be applicable for that particular well. So we choose. It's the same thing like we choose for the flow correlation for slippage. So if the flow correlation works for that well, then we try to use the same. If the Petrel, they use the Hagedorn drone, we try to use Hagedorn drone. So it will be compatible with the nodal. So that's the thing, yeah. So you can see the yellow here because you have some gas section. So of course, with the gas injection, the speed will decrease. Okay, this is just energy balance. So potential, friction, and kinetic energy. So it's the same like DVDC that we have, but DVDC in the variable. We are talking about the DVDC in the variable, delta P over delta Z. Nodal analysis for per nodal or for segment, etc. So it might be this one, delta P is potential energy, friction, and kinetic. And the mixture density, you can see rho bar is rho L, rho light, times the light phase soda, rho H times light. That's so average is I then copy.
thank you very much.
Silent copy is Vietnam, yeah. It's called
Just a local brand.
Just like Starbucks.
Starbucks logo.
Yeah. But they don't have the authentic Vietnam coffee like the coconut coffee. They don't have.
Ah,
They have the basic latte, Americano, things like this.
okay, okay.
They should have something localized, right?
So
Manis.
manis,
Apa tu? Americano?
Latte.
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 Very sweet, huh?
Sweet.
Okay.
Yeah.
I don't add sugar in my coffee, so
Yeah, usually, yeah, some are in Indonesia also, they like to have very sweet coffee. Yeah, they put sugar in coffee. Okay, so mixture density, yeah, we know that one. We can get from density tool, and or we can get from the hold up. If we know the hold up, we know the raw L, raw X, and we can get density tool. I mean density average of the mixture. So we get them. Okay, so that's thing. Okay, so we see what the nodal doing. I don't want to know. Let's keep going. So we have QOQT at the top, wellhead pressure. So the segment is just a nodal, for example, the first nodal at the top. So you have this one, so wellhead pressure minus delta P of the first nodal from the wellhead. And we know we have a PVD depending on the fluid and pressure temperature at the nodal. And then we can calculate the Q surface times the PO into this first nodal. So that's the QOQG at the first nodal, converting from QEQG surface. So you do it point per point, yeah. Then if you know the Q, you know the area, you know the velocity. So velocity of heavy, velocity of oil, velocity of gas, right? Of course, we base on the Q oil, Q gas at the surface. While we have PO and PG, we can put it into this plot. Yeah. So you know the oil on the Y, and gas on the X, so you know that point, you will be coming like this. So you know the slippage because we know the flow regime. Yes. We know the flow regime, we can calculate the slippage according to the flow regime.
Okay. This one we usually do a take from the emerald and do manually, or the emerald will do for it.
Emerald will do for you.
Okay.
This is just a nodal. I mean, that's the nodal. Nodal is not done in emerald. No, it's
Okay.
different way. But in principle, it's really almost similar. That's why we can explain something like this. So it's starting from the top to bottom, but in emerald, we going at bottom, going up the other way. But this is from the top to bottom, but the principle is almost the same. You have the Q, you have the velocity, you have the map, you know the slippage because you know the flow regime. Yeah, but in emerald, it's the other way. You need to know the flow regime to calculate the slippage based on the holdup.
Okay.
Yeah, so it's just three first thing. And then you have the correlation. Of course, the correlation with the map is will be different between the correlation. So based on the holdup, and you can see based on the holdup, you can get the density average, right? Then the density average, you put it in the equation here. You know the velocity from that one. U is the velocity, the average VM, that's the VM, not VO or VG. VM, you know the density out of the holdup, and you put that in, you know the delta P, and you put the delta P, P2, P is this one. So you have the delta P, then we have this one, minus delta P. So you do one by one. So this one will be done per segment, per nodal. So if you do that one, just step per step. So if it is okay, go into next step. If not, then just recalculate the correct delta P. So it's an iteration. So it's something like this. You have this one, this is calculated, yeah, the pressure. And then the second nodal will be calculated again, calculated again, calculated again. So until the bottom of pressure. With one for flow rating, with one flow correlation. But if you change the correlation, you might have a different pressure gradient. This is the nodal, and this is the nodal outlet. So you might get the MD, QOQG, etc. That's from the correlation. So from the correlation, we know the flow regime. From the flow regime, we calculate the slippage. So you have the delta P for different segments. So that's just the nodal, yeah, but we don't do the nodal in emerald. So for example, current you at constant wellhead pressure, yeah, you might have something like this. If you have a different hue or different correlation, if you put it in IPR VLP, you'll be having something like this. This is your VLP. If you have a different rate in the same tubing size or pipe size, and you will be having this VLP. And you plus IPR. So that point is the one that you're producing. Yeah, this is IPR VLP. It's not true. So like the first break, the first day I explained this one in order to increase the rate. This is the optimum flowing pressure. So if you want to get a higher rate, you need to have lower, or you have increased your RPR. So something like that. That's the technical operating. Okay, so we go to liquid-liquid correlation. So liquid means water, oil, water. The flow correlation we deal is only the fluid. Yeah, we don't talk about the solid. So we have only water, oil, gas. So three phase. Vertical is bubble flow. Yeah. So either water bubble in oil bubble in water. Usually oil and water is immiscible, cannot be together. But sometimes in the emulsion, you might get miscible. Not FOAMAP, yeah, sometimes you don't see FOAMAP. The correlation depend, they have some correlation can be get from the equation, mathematical equation, or from the lab. They have some flow loop, and then they have some experiment with the different velocity of different phase, so they come up with some equation. So it can be mathematical or can be from mechanistic from the lab. You have something? Okay, so it's just bubble gas. Yeah, it's the same that we see before. Just bubble of gas. Yeah, if you run tonal camera, you can actually see this one.
Mm.
But you need to be very clear liquid in the water. But if we have mixed, you cannot see. So if you have a bubble or something like this, or it's a lot of bubble like that, yeah. You see, once you know like this, you know the size of the bubble, you know the number of bubble, and you calculate the Q
Mm.
without the spinner. So you can do that by just looking at these bubbles and the number of bubbles in maybe 1 second, and you calculate the gas rate. You can do.
And that value is acceptable. That value is acceptable.
Yes, in instrument we do that. Yeah, we have in multi-prop tool entity processing, there are some calculation. So, but the thing is, with the whole camera, you can see the size of the bubble.
Mm.
But you might estimate, yeah, the bubble size maybe
Mm.
5 millimeters or so, whatever. So you can estimate the bubble, and then the number of bubbles you can detect. Remember, you have the needle, right?
Mm.
So you have the needle like this. Of course, the bubble,
Heating.
going into the needle, right? So in 1 second, maybe you have 100 bubbles.
The rates. Okay.
So yeah, we just estimate. Yeah, you can calculate. But of course, it's just the bubble passing through the needle. As you see, the needle is very small, and you have only 4 needle in, for example, in 7 inch or 5 inch tubing casing. So we miss quite a lot. Yeah, hopefully they are mixed. So if they are not mixing, then we miss them. We calculate maybe not correct. Yeah, it's underestimate. Um, so this is chocolate. This is liquid. We have chocolate ABB, Nicholas. So this is just, if you like to see the equation, just go to the paper. Yeah, we have, I think there is a PDF inside the Emerald program. So you go to Proplan files, you go into that one. If you want to get into more on these equations. Yeah, we're going to go down. So you know there's raw W and raw oil, this one, right? So that's why we need to get the density. So the slippage is based on the density difference. raw water minus raw oil. Yeah, raw water usually is higher than oil. And also 1 minus YW. So it's easy. If you have the density, you can just convert using this one. You know, the YH or Y water. So that if you put it on the plot, it will be something like this. If the difference is 0.1, for example, water is 1 gram per cc, oil is 0.9 gram per cc. So the difference is only 0.1. It could be, it's very heavy oil. So you might have something like this. So if you have higher difference, so of course higher slippage. Makes sense. Yeah. You can see on the axis water holder. On the left is 100% oil. On the right is 100% water. So it should be in between. Yeah. So if you do have higher water, you might be have higher slippage. But the thing is, on the left here, when you have no water, it's all oil. Yeah, we should not get any slippage, but then you still have some numbers there. So 2, 5, or 7. So token will be applicable if you are in high water holder.
Water.
In low water holder, you might be overestimated slippage. That's token. And you have some Nicholas.
Nicholas for oil or
It's the same.
the same?
It's just different name. I mean, different formula.
Formula.
The different formula. It's based on the experiments. Yeah. So you can calculate this one. You might have the YW as well. The velocity of limit is the starting to get the bubble, whereas the velocity start to get bubble is the limit. But still you need to get the raw, so water minus raw oil. So in this case will be at 11. That's Nicholas. So you might see that in the low water holder, preferable to use Nicholas. In high water holder, Port of the Moroccan, more or less.
I think Nicholas is like more accurate because it's when there is no
Starting from
water,
zero.
zero, and the water 100% still the same.
Yeah, that's okay, yes. Yes. Yeah. Okay. So that's liquid. So what we have here is we have chocolate, we have Nicolas, we have ABBs, extensions of the chocolate, coated really well. And Hassan Kabir, and also Groner. Groner can be used for horizontal work. So if the sleep is negative, you might be able to, I don't know if you can use Groner. So Hassan Kabir, you have a 3 flow regime: flow, slug, and churn. You can actually see on the flow correlation. Yeah, which color belong to which correlation. Yeah, so Choquette and Nicolas is based on the experiment. But Nicolas is only bubble flow regime. And then we have liquid gas correlation. Yeah, we have liquid gas correlation. So liquid usually is very small slippage, but liquid gas, really depending on the flow regime, you might have very different slippage. You have underground, you have doubler, you have 5 flow regime, etc. I think we have about 10 different liquid gas correlation. So some of the mechanistic is mathematical with the equation. So you derive from the equation, but some of them are from experiment from the lab,
Yeah.
from the flow loop. Yeah, they can do that. Okay, this is deviation. So for example, in the vertical, so on the axis deviation is vertical. So sleep rate is light phase velocity minus heavy phase velocity. So correlation is developed for vertical wells, and you can add up using some correlation. So you might get it up to 45 degrees deviation. Yeah. So with this one, so you have some equations to increase the velocity slippage up to 45%. Yeah, not percent, 45 degree. You might see the higher the deviation, the higher the slippage. But after 45 to 60 is decreasing. By then after 60 we are missing. We don't have any calculation. And in 90 degrees zero. Yeah, 90 degrees zero. So we are missing between 60 and 90. That's why we come with the multi-prop tool. Multi-prop tool, you can calculate qubits, but then just calculate directly light phase velocity, heavy phase velocity. So we don't need the slippage. Why we need the slippage? Because my spinner, our spinner is reading total velocity, but we need to know light phase, heavy phase velocity. That's why we divide into heavy and light phase velocity using the correlation. Depend on the flow regime, the slippage calculate. But up to 40 or 60 degrees. After that, there is no correlation can be used. So in that case, then we like to have your multi-prop tool. Yeah, since you have a multiple array or multiple sensors, probes, then we can directly calculate the Q for each different phase. Make sense?
Um, by looking at our data
Uh-huh.
at first, how do we determine our data, which regime is it?
It's difficult.
Difficult.
It's difficult.
We have to try.
Go to Emerald. You need to go to Emerald,
Okay.
choose the correlation, and we will see the flow
Try
regime.
one by one.
Yes,
The
you can
correlation.
choose. Yeah, you can choose. Yes.
Which one is suitable?
Yes.
Okay.
Yes.
Long way.
Hmm?
Long way to try one by one.
Not really try one by one, but you can just choose. For example, I mentioned if you use hackathon for nodal, you try to use the same for correlation hackathon for
Okay.
Emerald. So you might discuss with the reservoir or production engineer.
Okay.
So which correlation they usually use.
Okay.
So we try to use
The same.
similar.
Okay.
So the equation will be the same. Yeah. Or I think we do have a slide to choose which correlation to be used. I think in the last one. So I'll
Okay.
show you later on. Okay, so this is the place that we like to have. Again, so the slippage of deviated, yeah? 1 plus 0.04 times deviation. So it's maybe multiplied by some numbers. It's quite a high percentage of the deviation to the slippage. Yeah. So the deviation there is on angle and not radian. So if it is 45 times 0.04 is what? 0.14. So 1.2 is 20% increase. So it's big different. So it's definitely well, fax and real. Yeah, you may see the straight line or the revised boundaries they show. So this is different in the deviation or horizontal. So we mostly in the segregation flow region. In the vertical, we mostly on the bubble slug mist, right? But on the highly deviated or horizontal, we have a different flow regime. So it is different. Yeah. So you might have some different calculation as well for different slippages or different flow regimes. So the proton number, so Vm squared. So it's like the Vm, and we have the lambda. So Q liquid divided by Q total. So you have the percentage of liquid divided by Q total. So yeah, this is back samples. It's logarithmic. So that's for horizontal 90 degrees. So you might have some different things. You have some different formula. So this is the emerald that we have done, right? So well, we did this one. We have the red, we have the blue, we choose the gray, and we have done using the yellow and orange. Yeah. So what we are looking at now is the gray zone at the top. So you take the gray zone, you have the velocity, you have a density, and you have PT and PRA. The whole one. Yeah. Sorry, PRX is the density. That's the density. So we have velocity, density, pressure, temperature on that the gray zone at the top. Yeah, we see on the table we have PT, we have a PVT, we have velocity, and we have this one is two phase. So we have the density. We have density, we have velocity. So for each zone, for each gray zone, we have PVT because we have PNT. Yeah, for different grades. So we have to calculate Q total from where? Velocity times VGF, Vm times area. So we like to know the diameter or the ID for each different calculation. So yeah, I need to get the A there. So from the Q total, I need to get the heavy phase Q and light phase Q. And so heavy and light, you can get the velocity. So you put that velocity into the low regime, then we calculate the slippage. Yeah, it's almost the same like the model that we have seen. So, but from this one, you can have to hold up from the density, right? You can hold up the density from the hold up, might get the slippage velocity. Slippage velocity, you can get this point. From this point, you know the heavy phase and light phase velocity, and then you calculate the QH, QL. So it's the other way. Yeah. So you do for each calculation. So yeah. So you have hold up, you have the density, or yeah, this is the if you have the tool density, this is the one. Yeah. This is the average of your density reading. You know the hold up from your tool, example from capacitance. And then you have the rho L, rho X from your PVT. Then yeah, okay, sorry. You have this one from the tool reading. You have this one from the tool reading. Rho L, rho H are from the PVT. Yes, from the PVT. Then we can have the hold up. Because we know this one, we know that one, we know this calculated. From the whole part, we put into the correlation to get the slippage velocity. After the slippage velocity, we know the liquid and gas, and then we know the flow regime. So we calculate VH, from VH, we have QH, So from the top, you can QH, and then QH, as a thing. Yeah, this is from the tool, this is from the tool. You are knowing this one from PPT, from SOH, VL, VH from the slippage correlation, and yeah, you can calculate the order. So yeah, that's the thing.